Okay, so this is uniform circular motion. Instead of, I'll actually give you guys the lecture for your assignment this time. Let's say we have an object that's accelerating. Okay, so real quick review it. We're going to accelerate. And the thing with acceleration is, can you feel it? That's the whole point of acceleration. Can you feel it? All right, when you accelerate, what does it feel like when you accelerate? Okay, if you're in a car. Okay, if you're in a car and you step on the gas. Okay, what does it feel like to you? Okay, most people, when they're in a car, it feels like you get pushed back, you get left behind. You know, when the car accelerates, when you're in the car. And it's sort of counterintuitive. It's counter direction to where the direction you're going. You feel you're moving opposite to the direction that you're actually accelerating. Okay. Then we're going to talk about our centripetal acceleration. Okay, where AC equals v squared over r, and we're going to talk about period of rotation of a circle. Okay, so that's what we're covering today. All right, now we know that acceleration equals this. Acceleration is the limit as t approaches 0 of delta v, that is a delta v, not a delta r, a delta v over delta t. Okay, delta v is a vector. But what things can we change with vectors? Vectors have two parts to them, right? They have magnitude and they have direction. So we can change either of those things and create a change in our vector. Okay, if we change the magnitude, which is what we've been used to so far, if we change the magnitude of the acceleration, what are we really changing? Okay, it's the speed, right? The magnitude is the speed that we're changing. But we can also change okay. But what we've dealt with so far is if we change our velocity in a positive or negative direction, that just means we're slowing up or slowing down. We've talked about direction before. What we haven't really talked about is theta. If we change the actual angle that we're accelerating with, that becomes a different kind of acceleration. So, let's create a surface. Okay, and on our surface we're going to make a car. I spent some time making this car. Okay, it is a sports car. You know, because little cars just don't accelerate very well. Although toasters do. Okay, because I drive a toaster. You guys have? I do. My toaster's awesome. If our car has an acceleration to the left, okay, what do we feel when we accelerate? Okay, we feel that push backwards. When we feel like we are moving backwards when our car accelerates forwards. Okay, and it's like we're getting pushed back. Okay, at high velocity though, if we're just traveling fast, we don't feel much. Okay, imagine you're in an airplane. Okay, let's say you're taking off on the airplane, right? Okay, and it's when the airplane starts to accelerate down the tarmac, right? You get a pretty good acceleration. In fact, that you really feel that sink into your seat, and those are designed to absorb a lot of the acceleration, a lot of the forces that the bodies inside have. Okay, but you know when the pilot comes on, he says, "We have now reached a cruising altitude of 31,000 feet." Do you feel that? You don't. You're now free to walk about the country, right? You're not free to walk about the cabin. You don't feel the acceleration. You don't feel any motion in the plane. It's as if the plane isn't moving. You hear it. You feel a rumble. You know the plane's working, but you don't feel the fact that you're traveling at 600 miles an hour. 500 miles an hour. It's not there. The high velocity itself is not something that you feel. It is only when we change velocity that we actually feel something. Okay? And by the way, this is a very profound idea when we study relativity, is that how fast you are moving doesn't matter. It is only if your velocity is changing that truly matters. All right, and there is our next car. Now say we slam on the brakes. What is the direction of our acceleration here? Okay, it's backwards, and what does it feel like you want to do? You're going to go through the window if it wasn't there, or over the top of your convertible. All right, so our velocity, though, is still forward, yes? Slam on the brakes, we're still moving forward, but our acceleration is slowing us down to a stop, and it's going backwards. Okay, and what do we feel there? We feel shoved forward. Now, imagine we have a big parking lot, right? There's no speed bumps, no cars, no cops, no learning directors. Okay, what are you going to do? There's our parking lot. What are we going to do with our car? We're going to go out there and donuts. Oh, yeah. Let's do, although it would be interesting, because for some reason, donuts always attract the cops. It's, okay. Okay, but we're going to do our donuts at constant speed. We maintain a constant speed of our car while we are doing our donuts. Okay, in fact, let me do that one a little slower here. Oh, shoot. Ah! There we go. Let me slow. There we go. Let's do donuts. Okay, we go around and around and around doing our donuts. Okay, we just keep round and round. Okay, so there's our car, and we're traveling to the west in that part of our circle. Okay, we're looking from above. Okay, what do we feel when we drive in a circle? Okay, well, what we feel is like we're going to get thrown out of the car, right? Okay, we're going to get pushed out. Like the universe is telling us that we have to get out of the car, right? Get out. Okay, where we turn, and it's trying to shove you out the door, right? When you turn. Okay, well, what really happens if we base this on what we were just talking about, that if we feel like we have to move in the opposite direction to where the acceleration is, and we feel like we're going to be out of the car, right here. I like my hand. There's my hand. All right. If we feel like we're getting shoved out of the car, what's really happening is that our acceleration is in the other direction, right? And so instead of being shoved outwards, the acceleration is really inwards for where the car is moving. Okay, what if we're here? Where's the direction of our acceleration? Because if we're still turning, it still wants us, we want to go out, acceleration is going to be in, which points that way. Okay, and if we're at the other side of the circle, then acceleration is going to point where? Okay, it's going to point down for there, and if that's our velocity here, we can point. All of those are pointing towards the same point, right? Okay, that's an acceleration. It's also an acceleration that's perpendicular to our velocity all the time. This, in physics, is our definition of circular motion. It is when you have an acceleration that is perpendicular to your velocity and you're traveling at constant speed. Circular motion is defined by this, because there's no other way to have a circle unless you have these orthogonal vectors, unless you have A in a perpendicular direction to V. Okay, so let's repeat our, let's just get to the end here. There we go. All right, so here's our parking lot again. Okay. We call this acceleration centripetal. Centripetal means towards the center. And let me give you a different color here. Centripetal means towards the center. All right. So what happens if A isn't centripetal? Okay. Can we still move in a circle if A is not directed towards the center? Okay, well, what happens is we get a vector, an acceleration vector that's not pointed towards the middle, and all of a sudden, instead of being perpendicular to our velocity, we now have a component of that that's in the velocity direction, right? If it's on the angle, and what's that going to do to our velocity? Okay, it will increase our speed if we have a component of our acceleration that's in the direction of the velocity. And that component would take us out of circular motion. Okay? If we have a component of acceleration that's in the v direction, it's not constant speed, and therefore it's not circular motion anymore. Okay, you would start spiraling out if you increase that velocity. And this over here says the same thing as that. Okay. Okay, so if I need to step through this. Okay. So let's clean this up a little bit and say that we have an initial velocity here. And then we go a little bit further around the circle and we have a final velocity in this direction. Okay, how do we come up with this acceleration? Well, we're going to play a little geometry game here, and these, if we're maintaining constant speed, then what can you guys tell me about these two vectors? Okay, no, we're not getting there. If we maintain constant speed, and those are our velocity vectors, then they should have equal magnitude, or if we draw them, they should be the same length, right? Okay, so if this one's VI, our initial velocity, and that one's our final velocity, okay, then we draw this one, and that difference between the two is going to be, that's going to be our delta V, right? That would be our delta V. It's the VI plus delta V is going to give us V final, right? Our initial plus our change equals our final. All right, and these, because VF and VI are the same, this is an isosceles triangle. Yeah? All right. Now, we're going to do the same thing, except now we're going to do it with radii. Okay, so the radii that are pointing to the same points, and I guess that didn't show up very well on that one, because this should actually be this radius here. I didn't draw that well. Imagine that this point right here is actually right there. In fact, you know what? I'll just redo that. So I'll just make a new one. There. Okay. All right, and so we have our initial radius, and then our initial radius, our initial position vector, and then our final position vector. That's where they are in the circle. Yeah? Okay, then we're going to take then we get to make that vector right there, which is our change in our position, right? Okay, so at RF minus RI, okay, is going to give us this new vector, which is our delta R. That's delta R. All right, now we get to play some more geometry here. Oh, I still have to, okay. So, what we have here then are two, and I need to sit down for this. What we have here are two, they're both isosceles, right? Because we know that this leg right here and that leg are the same because they're both radii of the circle, right? Okay, we know that this is isosceles because the magnitudes of the, if we're moving at constant speed, the magnitudes of velocity are the same, right? Now, here's the cool thing. We also know that right in here, the angle between the radius and the tangential velocity is a right angle, yes? Yeah? So the angle between RI and VI, this angle right here, is a right angle because it's any radius to the tangent line is perpendicular. Okay, and we also have that over here. So let's take this group of vectors, the RI and VI, right? Okay, and imagine we rotate them up to there, right? So what does that tell us? Okay, it should tell us that this angle right here, all right, let's call it something like, oh, say, theta, okay, is the same as that angle there, right? Now, if these triangles are isosceles, which means that this angle, this angle here, these two angles are equal, and those two angles are equal, right? Then what can you tell me about these two triangles? They're similar triangles, right? Okay, so with that in mind, we're going to do this. We know that delta V, let me get my notes here. All right, the delta V over, okay, our final velocity is going to equal delta R over our final R, right? Or delta V over V is going to equal delta R over R. Yeah? Question? Okay, so we get this delta V over V equals delta R over R, right? That makes sense? Okay. Well, from here, I'm going to do a little manipulation, and we're going to do one, I'm going to multiply both of these by 1 over delta T, because I can do whatever I want as long as I do it to both sides. You with me here? And then I'm going to rearrange this a little bit, and I'm going to get 1 over V times delta V over delta T is going to equal 1 over R, delta R over delta T. You with me there? All right, now comes the fun part. This, we're going to take the limit as delta T approaches 0, not theta, 0, right? So what does that give us? this should give us 1 over r. Okay, and what is dv over dt as delta t approaches 0? That's our acceleration, right? That's our instantaneous. Okay, so that's going to be times a. Okay, equals 1 over. I'm sorry, this is not r. This is v. Hold on, guys. This is v. Makes a difference. Okay, equals 1 over r times, and what is delta r over delta t? Okay, that's our velocity, right? Okay. What we're going to do is we're going to solve this for a. So I'm going to move up so I have some space here. If we solve this for a, okay, we're going to multiply both sides by v, right? To solve for a, and we get a equals v squared over r, v squared over r, and this is the magnitude of our acceleration when we travel in a circle. Yeah? Okay, this becomes, so if we put a little c there, this is our centripetal acceleration. This is the magnitude of our centripetal acceleration when we are traveling at constant speed in a circle. Okay, or I should say, this is the magnitude of our centripetal acceleration at any given moment if we're traveling on a curve. You follow? So it's our speed along the curve squared divided by the radius of curvature gives us our centripetal acceleration at that point. Is another way of looking at it. Okay. Last thing I want to talk about. If we've got our circle, okay, here's our circle. And we travel around the circle. We start here and we're going around the circle, we're going around the circle, around the circle, around the circle. Our speed equals distance over time, yeah? Distance over time. Okay, but how far is our distance? Okay, in any particular, if we're just looking at one time around the circle, what's our distance? Equals 2 pi r, right? Over. Now, the concept of the time it takes to go around the circle one time is called the period. It is the period of rotation, or anything that has a periodic function has this t to it. We call it t. And we will call this, it's a capital T, and capital T is the period of rotation. Okay. Now, if we call our speed v, if we want to find our period of rotation, then we get a period equals then 2 pi r over v, and that's our formula for a period of rotation. Okay, so real quick review. When we accelerate, When we accelerate, we generally feel it in the opposite direction. So if we're accelerating forward, we feel ourselves moving backwards. When we're slamming on the brakes, we want to keep moving forward, even though we're being pushed back. Okay. Using that concept, we get to our donuts, and we know that if we're traveling in a straight line in a circle, okay, when we're traveling in a circle, but our velocity is at a constant speed, and when we're turning, we feel we want to go to the outside, which means that the acceleration is to the inside. No matter where we are on the circle, acceleration is to the inside. Okay? And if our acceleration isn't centripetal, then we don't have a constant circular motion. We would have something that would spiral out like that. Okay? Which brings us to, okay, that gives us our centripetal acceleration through our triangles, and then we have our period of motion. Okay? So that is it for today, and now you have enough information to do your homework.